All right, 8.8. We're taking a look at something called improper integrals. This is our last section in Chapter 8. It's going to finish up something that we have seen happen back in, well, not finish up, at least continue on, something we saw happen in Calc 1 and something we saw happen in Chapter 5 and Calc 2. Okay, so it's going to involve both of those pieces. And in particular, what it's going to involve is limits that approach infinity. Okay, do you remember doing that? My Calc 1 class just got through with a test question on that. They're struggling, okay? So if you don't remember it, it's okay. We're going to go back over it a little bit. And then we saw something happen with this in section, I think they called it 5.6, something like that in Chapter 5, where we had some limits with infinity going on as well. So we have seen that again this semester. So what I want you to first recall is that when we have an integral from a to b of f of x dx, we call this a definite integral. Okay, a definite integral. Now, this section is supposed to be talking about improper integrals, so what is the difference? Well, improper integrals either have, one, limits of integration where the a or the b actually says infinity or negative infinity. That's one option. In this case, we use limits to find the value of those improper integrals, and you'll see how that works. The second option is that we potentially might have we would have, right, of the two options, a discontinuity within the interval ab for our real numbers a and b. For example, a real quick picture of where you've seen this happen is if we were trying to integrate 1 over x from -1 to 1, like this, and we just tried to do it with our normal properties, we'd get a value and we'd get an answer and it would be wrong. And the reason it would be wrong is because it's not continuous. And the definite integral formula hinged on the function being continuous. And if we have 1 over x, it looks like this. And in particular, here's -1 and here's 1. And it has got an asymptote that happens between those two values. So it's typically an asymptote that's causing a problem. That's sort of a red flag thing to look for. In theory, it could be more discontinuity kind of things than just that. But asymptotes are typically our problem spot. Okay? So this is what's happening if we're taking a look at the second part of this example, or this definition or whatever description. The first one is that you'll actually see an infinity present. Okay? So we're going to see examples of both varieties. I think I have 3 or 4 examples, I think, for today on this section. And the first variety is going to be variety number 1, where we've got an infinity present. Okay? You ready to try it? All right. So this looks like something you could do if either it didn't have limits of integration at all, or if they were both numbers. You've seen this kind of thing before, right? Yeah, the integral itself is not the challenging part. The question is, what do we do with the fact that there's an infinity up there? Because infinity is not a number, right? We sometimes sort of think in our mind like it is, or we sort of want to operate with it like it is, but you can't plug infinity in for anything. And for those of you who are continuing on into Calc 3, we'll revisit this idea again. Infinity is not a number. You can't plug it in for something. So we need another method by which we can approach what happens when there's an infinite limit. And what that is that, or an infinite upper bound or lower bound. And what that is that we use limits. So we're actually going to rewrite this as the limit as, and the typical convention is to use the letter b. I'm not really sure why it's necessarily a b. You used a different letter, it would not be the end of the world. The b is our normal convention, and we rewrite this where the b is simply taking the place of where the infinity originally was. It's probably also appropriate to be aware of the fact that we don't have an asymptote on this interval from 1 to infinity, right? There is an asymptote for this function, but it's at 0, and it's outside of the interval. So while it has an asymptote just like this one over here that I mentioned, it's not on the interval, so it's not a problem. Okay? So there is one, it's just not on our interval. So the infinity at the top is the only problem that we have. And we're going to take the antiderivative of this just like we would for anything else at this point. And we have this b here, and I'm going to just rewrite it first as 3x to the -5. All right, so what is the antiderivative of 3x to the -5? 3x to the -4 over -4. Everybody good with that? Okay, so just like in Calc 1 and just like in Chapter 5, every single time you're going to write limit, right? because one line is equal to the next and the limit has not gone away. It's kind of like if you had a square root on a problem. You don't just leave the square root off and then put it back on at the end and think that all the steps in between were equal. Every single time you write the square root until you actually take the square root. The limit's acting the same way. So we have a limit as b goes to infinity in front. And we do have, I should say, we do not need to have, that's what I meant to say, a plus c on this one. Do you know why? Because we're doing a definite integral, right? I mean, like in the sense that at least it's got an upper and a lower limit. So we won't need a plus c. When we start evaluating things into functions, we don't do the plus c's. All right, so I'm going to rewrite this as, let's see, we would have, 3 over negative 4x to the fourth. Does that look okay? All right. And then on all of these, what we would have done is, when we're doing definite integrals, is we would have evaluated them at the upper and the lower limit, the b and the 1. So what does that look like? Let me shrink this and shift it over a little bit. Well, if we're taking a look at what we do on this, we're going to keep writing the limit, b goes to infinity, and we're going to take the b and we're going to actually, plug it in for the x. Okay, so it looks just like what we would do if it were a number there. So I have 3 over negative 4b to the fourth. Everybody good? And then I do the same thing with the lower limit, the number 1. I have minus, and I have 3 over negative 4 times 1 to the fourth. Now, the second piece is, it's not that it's irrelevant, but it's something we've done before. It's not something new. You just simplify it, you get a number. In fact, what does that number become over here, just for the sake of doing it? 3/4, right? Yes? Okay, nods are good. Yes, 3/4, wonderful. Okay, now think about what happens as we let the value of b go to infinity. If you have 3 over negative 4b to the fourth, and the b value is getting infinitely larger, that means you're dividing by something that's getting bigger and bigger and bigger. What happens? It goes to 0. And in fact, back in chapter 3, when we learned this last semester, that's a theorem that we had. That if it's ever written as a constant over a power of x, we'll say x to the k, like this, and the limit, and this has the limit as x goes to infinity, that this is equal to 0. That's a theorem that we had. So anytime this property happens, this actually gives us a 0 here. And then what happens when we add 0 and 3/4? We get 3/4. Okay, so the 3/4 matters. It's just that it's not that it's a difficult question. Now let's go back up to the directions that I didn't read. Hopefully you did. But I want you to understand what we just did is the right approach, even though the directions sound like it's asked backwards. It says we're going to decide if it converges or diverges. And if it converges, we want to evaluate it. That's the directions, that's the order of the directions, right? And they always list them like that. But the way we decide if something converges or diverges is that we attempt to evaluate it. And if we get a number, then it converges and we've evaluated it. We've done both at the same time. And if we end up getting something that's infinite, then it will diverge. Y'all okay? This will happen again in chapter 9 in our textbook, where we do this approach, where it says something like this. It says evaluate, or it says decide if it converges or diverges, and if it converges, evaluate it. But you don't really do it in that order. You attempt to evaluate, and in evaluating, you make the decision about whether it converges or diverges. So what will this one do? It will converge. Why does it converge? Because it got a number. That's why. It converges. Okay, ready to try another one? All right, I got another infinity up here, right? So the approach is going to be quite similar. I'll actually start down here since I knew I ran out of space last time. We're going to make the limit as b goes to infinity of the integral from 4 to b, and I have 1 over x times the natural log of x cubed dx. All right, so now I'm at the point where we've been working all in this entire chapter, and back in chapter 5 as well at the beginning. I need to take an antiderivative. So how do I take an antiderivative, or what approach would I need to use when I have this form? It is u substitution. Sophia, do you know what you would like to let your u be? Sounds good. U would be the natural log of x because du is 1 over x, and that's part of my problem already, correct? We'll put the dx on the end. So I'm going to take what I have here and I'm going to change it into a u substitution, or I'm going to change it using u's. The limit as b goes to infinity stays in the front. Now, when we did definite integrals with u substitution for the first time in chapter 4, we talked about the fact that there's two ways to do this. We can either leave the limits of integration off, which is the way I'm always going to do it, or you can actually change the limits of integration based on the change of variable that you've made. So my inclination always is to just leave it off because it mimics what we do with the other things a little bit more closely. So I'm going to leave it off. I won't put the 4 and I won't put the b. They're just going to remain off for the moment. And I'm going to make my substitution. The 1 over x dx gets replaced with the du, which I'll put at the end. And then the natural log of x gets replaced with the u, and it's cubed. Okay, is that all right? But of course, the very nice way to write this for what we're going to be doing is going to be that we can rewrite this as u to the negative 3 du. Okay, everybody good? All right. What is the antiderivative of u to the negative third? U to the negative 2 over negative 2. And if I rewrite that in our maybe a little bit more standard notation form with a positive exponent, it would look like this. Is everybody good so far? Okay, what do I need to do after this step? I need the limits of integration, but there's something to do before that. Yeah, I need to put the u back in as x. Okay, before I do my the limit as x goes to, or as b goes to infinity, I need it to be back in terms of x. So we're going to put this back in, limit as b goes to infinity of 1 over negative 2 natural log of x squared. And then I can do my limits of integration. Like Adrienne said, I've got a b on top and I have a 4 on bottom. Okay, it's probably also worth noting natural log itself is also only defined from 0 to infinity, and you can't use 0 as a limit of integration, but that's not a problem because this went from 4 to infinity, so we're good on that count. And we're going to put in to this the b and the b and the 4. So this is natural log of b squared, and then plus, and I have 1 over negative 2 times the natural log of 4 squared. So the part where I put in the number at the end, that's never the problem. I mean, like, that's not the place where we need to spend our focusing time. Our time is focusing on what's happening here. Now, this does not have the same form that I had over here. It's not a constant over x to a power. So I can't just say it works just like that. I need to be a little bit more careful and pay attention to what this graph actually looks like. And in particular, I want to think about what happens to the graph of logs. Okay, because whatever's happening, it's going to be squared and multiplied by a number, but it's whatever's happening to log that's going to determine it. Sophia, do you have a question? Did I write something wrong?
Is it plus?
Oh, right here, it's minus. Thank you. It is, you're right. I keep pressing copy. Cut, minus, thank you. You're right. So this one will change signs to both positives when I make amends for that. That's true. Okay. So do you know what the graph of log looks like? Do you remember? We did it back in chapter 5. Some of you are throwing your hands up and putting things up that look really good. So I think we're going to really hope. Is this what we're remembering? Wonderful. That's fantastic. Okay. This is the basic graph of what happens with log, right? So as the x value goes to infinity, or in this case, we're looking at the b, right? But as we go to infinity on the log curve, what value are we getting close to? Or what's happening to my values? They're increasing. They're increasing slowly, but they are increasing. They are going to infinity. So this natural log graph, when I talk about the natural log of b here, as b goes to infinity, this number goes to infinity. And if I take something infinite and I square it, it's going to still be infinite. And if I multiply it by a negative 2, now it'll be infinite but negative. That's okay. So this entire denominator is approaching negative infinity, right? That's what's going on. And what happens when you divide the number 1 by something that's getting infinitely negative? It's still 0, just like the last problem that we did, right? So this one, out of space, one more time. This one does what the last one did. This is 0. And then I have whatever this crazy number here is at the end, right? 2 times the natural log of 4 squared, right, like that is my value. And I don't necessarily know what that value is, and there's really no cleaner way of writing it aside from like approximating it with a decimal. But it's a number, yeah? It's a number. So the part that I've just boxed in, because I'm adding it to 0, is going to be the sum, right? It's going to be the integration that I'm looking for. So will this converge or diverge? It's going to converge again, right? Again, because I got a number in this spot. It's going to converge. Ready for the next one?
Is the next one going to diverge?
I don't know. We're about to find out. I got to have one somewhere along here at least that does, right? That's the goal when I create things, is to show you some variations. There's something else that's different about this one, though.
That's 0.
Okay, so the lower limit's 0, and if I tried to plug 0 into the x right here, it would be undefined. That's a problem. You also probably should notice that there's no infinities here, right? So this is actually case 2, right? It's got something that actually is not evaluated. It's not on the domain. It's not continuous there, those kinds of issues. Everybody good with that? So when I look at this one and I take my approach here, I can't just put the 5 and the 0 in. I actually have to recognize that I would not be able to evaluate this as 0, like ever. Like that's not going to work. So whether you recognize it at the beginning or whether at some point later on you're like, oh crap, I can't put 0 in here, you're going to have a limit show up somewhere. So if you don't actually recognize this one at the beginning, it's not a big deal, but eventually you're going to have to insert the limit. We've recognized it at the beginning, so I'm going to put it in here right now. So this is going to be the limit as b goes to 0 this time. And then I have the b to 5. And while I'm doing this, I'm going to go ahead and rewrite. Actually, I'm going to leave this as 10 over x on this one. Yes. Okay. 10 over x. What's the antiderivative of 10 over x? Ah, very good. So this one, limit as b goes to infinity still. That's not a good infinity. Let's try it again. And I would get the natural log of, technically it's, oh, I've left my 10 out. Let me get my 10 in there. 10, natural log. Technically it's the absolute value of x. I could choose to leave that off and just write natural log of x in this one, though, if I wished. Why? What did I do wrong?
Infinity.
Oh, I wrote infinity for my last one. Thank you. Man, I can't get my copy paste to work here for me today. 0. There we go. Thank you. I could leave the absolute values off. Why?
It's not negative.
Yeah, there's no negatives I'm going to be trying to plug in, right? My limits of integration started at 0 and went to 5, right? 0 to 5 are positive numbers. So if I left the absolute values off on this particular one, it would be okay. And your default of just putting them on all the time, you can leave them on as well. So they don't have to be there on this one. We can take this now as b goes to infinity. Still not infinity, still 0. And we're going to evaluate this from 5 down to b, right? So we're going to put the 5 in first. So this is going to be 10 natural log of 5. I will leave it off now. And then minus 10 natural log of b. Okay, we already looked at the natural log graph just a moment ago, right? It was over here. Looks like this. So the first piece now, this is a number. If you wanted to rewrite it, it could be rewritten as the natural log of 5 to the power 10. That's fine too, but it's a number. Whatever this is a number. What happens if we put 0 or attempt to put 0 into natural log? Okay, so on this graph, we're not looking at this part of the graph now, right? Does everybody see that? We're looking at this part of the graph. because my b value is attempting to approach 0, not approach infinity. So over here, we're doing this. We're plummeting. That value that it's approaching then, I have 10 natural log of 5, is actually approaching negative infinity. So, I mean, yes, I do have negative and positive here, and this is infinite, right? So I now have some number to which I'm adding infinity, which means it's infinite, right? The whole thing is infinite. And I'm sure I said this last semester when we talked about these infinite limits, but this is like when the child tells you, I love you to infinity, and you say, I love you to infinity times infinity. That's still infinity, right? Now, if you ever decide that you want to take some analysis course, you're going to learn that there are different values of infinity. This isn't going to matter for what we're doing right now, but there are different levels of infinity. It's infinite, right? It is infinite. What does that mean? Converge or diverge? It diverges. So make sure that you're actually stating that. I'm suspecting inside of WebAssign there's like a multiple choice part where you're going to have to pick one. It's probably not going to be something you have to remember. It'll just probably be there, but it does diverge. So it's infinite, it diverges. So if we get infinity or negative infinity, we get that it diverges. Okay, I have one more. What about this one is similar, and what is different to what we did before?
Constant over x.
Constant over x, that's similar, right? We had 10 over x, this is 3 over x. That's pretty much the same thing. What's different? What's that? It has an infinity in it. The last one didn't.
Does not start at 0.
And it doesn't start at 0. So it was the 0 that was causing problems on C, right? At least not necessarily problems, but it's what put it into this section, right? The 0 lower limit is why it's inside of section 8.8. But over here, there's not a 0 that's causing that to happen. It's the infinity again that's causing it to happen. Okay, so let's actually take a look at how we rewrite this one. It looks much like some earlier ones that we have done, combined with a little bit of the last one. So the limit as b goes to infinity, I have 1 to b of 3 over x dx. What is the antiderivative of 3 over x? Yep, 3 natural log x, with or without the absolute values, your choice. It doesn't need it because the limits we're about to put in are positive. If you put them there, it would be fine if you did too, right? So either way is fine. We're going to put this in then. I have the limit as b goes to infinity of 3 natural log b minus 3 natural log 1. Interestingly enough, what is 3 natural log 1? Somebody said it. It's 0. The natural log of 1 is the number 0. It doesn't really matter. It's a number, right? So you can figure out whatever that is, or it can maybe not simplify if it said natural log of 2 or whatever. But it is 0. What happens in the natural log graph then? Oh, I don't think I still have it copied over here. What happens on this natural log graph then if we're taking a look as b goes to infinity? It's going up this time, right? It's going like this. Again, really slowly, but we end up getting infinity for that piece. So this one's infinite, so infinity minus 0, which is still infinity, which also means it diverges. Now, you might think, okay, well, that wasn't very exciting, but I want to show you what that's actually telling you about this graph. Generally speaking, whether we're looking at 10 over x or 3 over x, they have the same basic shape, right? And they have a shape that I've actually drawn today. They're approximately like the 1 over x graph too. And I'm only looking at the right-hand side because I've only looked at numbers from 0 to 5 or from 1 to infinity. So it's only the right-hand side of the graph that I care about. So in one of our questions, we actually went from 0 to 5, which means we're finding this area like this. And you might look at that and say, well, obviously that's infinity. That thing's shooting up to infinity. Of course we're going to get an infinite value. Interestingly enough, if you did this graph or this equation, but it wasn't 3 over x or 10 over x, but it was 3 over x squared or 10 over x squared, you might not get the same result. In particular, the second graph that we looked at started at 1. and it did this, right? We found this area. This area is also infinite. This is the second one we did. This is D. This is infinity too. That's what we found out. That's a little bit less intuitive. You might be looking at that and thinking, well, that tapers off to 0. Eventually, it's adding so very little every time. It should sort of stop, right? It should sort of stop adding things to it, but it doesn't. And it's this case exactly that if we did x squared, that we would see something different happening. So let's pause for a moment, take this exact same equation, but let's do it as 3 over x squared instead of 3 over x. Are you with me? So we're doing the exact same thing we did before. I don't have a nice new screen. It's just going to be plain old white. But we're going to have the integral from 1 to infinity of 3 over x squared, which looks almost stinking exactly the same. Like, it's practically not different at all. If you graph it on your calculator, you're going to be like, this is the same graph. I mean, like, it's just no different. So let's give it a try. This is going to be the limit as b goes to infinity of the integral from 1 to b. And I am going to rewrite this as 3x to the negative 2 dx. All right, what's the antiderivative of 3x to the negative 2? 3x to the negative 1 over negative 1. I'm going to take a moment to rewrite that as negative 1 over 3x, and we're evaluating from b down to 1. Okay, does that look okay so far? Did I get all my pieces in there right? Nope, I moved my 3. Good grief. All right, do I have all the pieces in there right now? I think so. All right, we're going to put our b in. So this is negative 3 over b. And then minus a negative, so I'm going to have a plus, and it would be 3 over 1. Okay, so this piece right here at the end, of course, is 3. So that's fine. What happens here? It's getting infinitely small, right? The infinity's in the denominator. This matched that form back in chapter 3 that we talked about from ages ago. It's a number over x to a constant. The constant's 1. It's not very exciting, but this is infinitely big in the denominator. When you divide a constant by something that gets infinitely big, it approaches 0. This converges. It converges. I'd like for you to graph this real quick, okay? Take your calculator, and I'd like for you to graph like y1, 3 over x, and y2, 3 over x squared. They're not identical, obviously. If this one is 3 over x squared, 3 over x, the original graph, what happens when you do 3 over x squared? How does that graph compare? It's going to be similar, but what's it going to be different? It's a little bit lower, right? It's a little bit lower, and really we only care about what happens as you go from 1 to sort of infinite, right? Like over this direction. So I'll draw it in a different color. Let's draw it blue. It'll be a graph that, again, on the part that I care about, it's cutting just a tiniest bit lower. Almost negligibly so, probably, if you're looking on your calculator, right? And the black one on top has infinity area underneath it, if you want to think about it that way. And the blue one has an area of 3. That's crazy. That should feel a little uncomfortable. I hope it does. Because that's not an intuitive math result, is it? It's not intuitive. And we see this happen again in chapter 9 in Calc 3, where there's a very intuitive, analogous result to this, where it feels like that doesn't really seem like it should be that way, and it actually is. Crazy, right? All right, that's it for today.